Good morning, everyone. Good morning, Bacha. How are you? My voice is clear now. Good morning, Sujan. Is my voice clear? Okay, Chachmi. So let's start our today's session. This is about semiconductor physics. Okay, so let's start about this. Sorry. So these are the topics that we are going to cover, and most of the topics we will cover today. If something remains, then we will take care of that in the next class. So first of all, what is energy band in solids? When we talk about energy bands, the thing is written on your screen, but I will take some amount of time explain this. In the previous chapter of atoms, what we have studied that every atom or in every orbit, electron has different energy. That's what we have studied. Like in hydrogen atom, the energy levels were in ground state, that energy is minus 13.6 electron volt. In second orbit, n equals to 2, you can say the energy is minus 3.4 electron volt. So in every orbit, electron has some different energy. And these energies are called as energy levels. But when we talk about solids, the atoms are very close to each other. Like for example, this is a atom of solid, nucleus, and these are the orbits. Something like that. Now this is another atom which has similar orbits. Now what happens? The orbits, or you can say the outer orbits of two close atoms or nearby atoms interact with each other. That means electrons present in the outer orbits start interacting more with the nearby atom. So by this way or in this way, the energy levels of the particular shell changes. What I am saying, but in solids, when atoms come close to each other, there is a shift in this energy level of a particular shell. Why this is changing? Because of the interaction of the nearby atoms. For a particular shell, energy levels of a particular shell may rise or fall. That means this energy level that was fixed already in, if atom is isolated, may change, may increase or decrease. The collection of all these variations is called as energy band. That means, for example, if I talk about there is a 1s, you know that 1s, 2s, 2p, I think you have heard that in chemistry. So let's suppose this is the energy level of 1s. But due to the interaction with nearby atoms, this is not 15, this is 1s. Okay. Due to the interaction with the nearby atoms, its energy may increase or decrease. It may increase for few atoms, it may decrease for few atoms. And this collection is known as energy band. So this is the energy band of 1s cell. Similarly, there will be energy band collection or energy band of 2s. This is the energy level or energy band of 2s. Similarly, it can be formed for many different levels. So in energy bands, I think one thing is clear. This energy band formation is due to the interaction of the nearby atoms. And it is a collection of energy levels. I think it is clear. Now there is a one more punchline that you can study here. You can see here what you can see. Energy levels of outermost cells are most affected by the interaction of closely packed atoms. Why outermost cells? Because you can see that these outermost shells are very close to each other. That's why in outermost cells, the interaction is more and they are most affected. That means as you move up, the higher band will be of larger size. This is 2p. Similarly, if you move for 3s, it will be more larger. That's why they are larger in size. They are becoming larger due to the interaction. One thing is clear. Now, one more thing. These energy bands are categorized in two ways, generally valence band and conduction band. What is valence band? Like in this, you can see that 1s, 2s, 2p, similarly other bands. And you know that by chemistry that these are filled. First of all, 1s is filled, then second s will filled, then 2p will be filled. Let's suppose up to 2s atoms are electrons are filled. Let's suppose I'm just assuming things to not create a longer series. So up to 2s electrons are filled and 2p is completely empty. So what is valence band? The band or the highest band which is completely filled. So 1s is already filled, 2s is already filled, but out of these two, 2s is higher. So if it is higher position, then this band is known as valence band. So what is the definition of valence band? The highest energy band which is filled is called valence band. And then what is conduction band? The lowest unfilled energy band just above the valence band is called conduction band. So from this conclusion, what we can draw, if this is the valence band, then the band just above it is called conduction band. Conduction band. And there is a very small amount of gap. This gap depends on the material with which you are dealing. If it is an insulator, this gap will be larger. If it is a semiconductor, this gap will be of some moderate size. And if it is a conductor, this gap is negligible. I am talking about this gap. This gap is known as forbidden energy gap or generally energy gap. I think definition of both the bands is clear. Now, one more thing. Remember in mind, the electrons generally are in this valence band. When some extra energy is given, the electrons jumps from valence band to the conduction band. Listen, after receiving energy, electrons may jump to the conduction band. This band means conduction band. And when they jump from valence band to conduction band, one thing to be remembered again, when they jump, let's suppose you have given some heat and the electrons have jumped to this band like this. The electrons have jumped from valence band to conduction band. They, in place of its space, they have created a hole. They left a hole behind. Hole is nothing but a space of electron. This is a hole. They left a hole behind it. So what I'm saying, after receiving energy, electrons may jump to this band. Now, one more thing. The electron which has reached this conduction band is now a free electron. Is now a free electron. It will treat like a free electron. I think in this screen or in this slide, every point is clear to you. What is valence band? The lowest, the highest filled band. And what is conduction band? The lowest unfilled band. Electrons may jump between these two bands. And electrons in the conduction band are called free electrons. They are free to move. Moving further. The energy gap I have explained you already. I think you can see the definition and the thing I have explained already. This gap is known as band gap. This gap is known as band gap, and depending on this, materials are classified. Insulator has larger gap. Semiconductor has some moderate gap, and conductor has negligible gap. Now, what are the types of semiconductor? Generally, you can see semiconductor materials are formed using silicon or germanium. Silicon and germanium. These are the two widely used semiconductor materials. Now, there are two varieties of semiconductor. One is intrinsic, other is extrinsic. So if I talk about intrinsic semiconductor, these are the pure semiconductor. These are the pure semiconductor. That means silicon in its pure form is known as intrinsic semiconductor. Now I will show you a little bit of detail about it. Let's suppose we are talking about silicon semiconductor. So what happens? Silicon has 4 electrons in its outer shell. It's in the 14th group, I think you know. So it has 4 electrons in its outer shell. When silicon crystal is formed, it forms a tetrahedral bond with nearby silicon atoms. Every silicon atom has 4 electrons like this. So what it does, it makes bonds with a tetrahedral shape of bonds formed with the nearby silicon atoms like this. These red are the bonds formed by the silicon. Now everything is complete, no problem with that. But as soon as you increase the temperature, you reach the somehow room temperature of 25, 27, near about this temperature. What happens? Some energy is received by these electrons, and some of these electrons breaks the bond and becomes free and jumps to the conduction band. This everything is in the valence band. When you increase the temperature or when you you have given some extra heat, then in that case these bonds break. And when the bond break, one electron becomes free and reaches to the conduction band and leaves behind a hole. Leaves behind a hole. This is the actual process of intrinsic semiconductor. However, at room temperature, the bonds are broken, lot of bonds are broken, but the overall, if you see, the number of electrons are very small. This can also be represented using band diagram. And remember this band diagram. This is okay. Can you tell me which band is this one? Which band is this one? You can write it in short. Which band is this one? Okay, Veena, it's conduction band. Very good. Chishani, you have mentioned it wrong. This is conduction band. Na? This is valence band. Very good. Now, what happens at room temperature? I am writing at room temperature. Some of the bonds are broken and electrons have jumped to the conduction band and leaves behind a hole. So in intrinsic semiconductor, one more characteristic property is that the number of electrons in the conduction band are equal to the number of holes in the valence band. So that is again a punchline that can be written for intrinsic semiconductor, that number of electrons are equals to number of holes. Okay, Chechuni, no problem. Aishi is also correct. Conduction band. So is this point clear? Why number of electrons and number of holes are equal in intrinsic semiconductor? Intrinsic means pure semiconductor, because in conduction band, electrons reaches after breaking the bond, and the number of bonds broken is the same number of holes created. So is this thing clear? However, these electrons and holes both are called as charge carriers. Mark every point. Electrons and holes are called as charge carriers. This point is also clear. Charge carrier means they are responsible for the current. They are responsible for the current. Make or write every point. Now, one more point I will say. Electrons are swift to move. Swift means they can move quickly, they can move freely because they are generally known as free electrons. But these holes cannot move freely. Cannot move freely. So you can say mobility, this is the mobility of electrons is more than the mobility of holes. These all are the punchlines that I am telling you. Okay, let me repeat it once again very quickly. Silicon and germanium are generally pure semiconductor materials. One point is clear. When silicon is used as a semiconductor material, it forms a tetrahedral shape and forms covalent bond with the nearby silicon atoms. At room temperature, these bonds may break. Electrons may jump to the conduction band, leaving behind a hole. So number of electrons and number of holes are equal. Holes are nothing. They are a space for electron. But generally, we treat them as a positive charge. Generally, we treat them as a positive charge, but they are not positive charge. They are nothing. They are just a space of electron. But we can treat them as a positive charge, and I can explain it, but it will take a lot of time. So I'm not going with that. You can remember this thing that we can treat them as a positive charge, but they are nothing. They are just nothing. Moving further. After this, extrinsic semiconductor. Now, extrinsic semiconductor is what? The semiconductors with some intentionally added impurities in it. Now, when you add some impurity, why we are adding some impurity in the pure semiconductor? Because I have told you that number of charge carriers, that electrons and holes were very small. When they are very small, the current they will form will also be very small of negligible use. So we want more current out of these semiconductors. That's why we have added some impurities. That's why we have added some impurities. And the process of adding impurities is called, can anyone tell me? What is this process called as? The process of adding impurity? Anyone knows? Say yes, no. Doping. Very good, Veena. Very good. This process of adding impurity is called as doping. Very good. Now, you know what is doping. Now, after moving this, there are two types of extrinsic semiconductor. One is N-type, one is P-type. So if I talk about N-type semiconductor, now listen to me. You have intrinsic semiconductor, intrinsic semiconductor. Now add some pentavalent impurity. And if you add some pentavalent impurity, it will become N-type semiconductor. So one is the punchline. How N-type semiconductor can be formed? By adding some pentavalent impurity. Pentavalent impurity, I mean 15th group of your periodic table. 15th group is what? Nitrogen, phosphorus, arsenic, antimony, bismuth. I think, is it correct? This is your 15th group now. Okay. So what happens? I will give you a very quick look of that so that you can understand everything here. N-type semiconductor, if I talk about, when you add, let's suppose I am adding phosphorus as an impurity. So when you add phosphorus, it replaces the central atom of silicon. Phosphorus has 5 electrons in its outer shell, 3, 4, and 5. These 5 electrons, out of the 5 electrons, 4 forms the bond with the silicon and 1 remains free. You can see that these 4 bonds are formed, nothing has changed, but 1 electron is remaining free. So this one electron, which is free, is generally donated. Now I will explain you what happens after this. This is again conduction band. This is valence band. I am drawing these conduction band and valence band for the silicon. This is conduction band, valence band, and these both are for silicon. Now what happens? The extra free electron of phosphorus has some energy, because electrons has some energy in their orbits. So the energy of this extra electron or this phosphorus electron is just below the conduction band of silicon. Now you can remember this thing. The energy level of phosphorus atom or phosphorus electron is just below the conduction band. So at room temperature, what happens? One thing that is very common at room temperature, what happens? These electrons from the valence band breaks a bond and jumps to the conduction band. This is a very common process that we have studied in pure semiconductor. Nothing changes. So holes are created in it, electrons are reaching conduction band. But at room temperature, these electrons which are just below the conduction band requires very less amount of energy, this much amount of energy to reach the conduction band. So all these electrons jumps to the conduction band. All these electrons jumps to the conduction band. And when they jumps to the conduction band, you can see there is a lot of electrons in the conduction band. But the number of holes in the valence band are very small. That's why this phosphorus is known as donor impurity. It is generally called as donor impurity. Why donor? Because it has donated its electrons to the conduction band of silicon. One thing, this is called as donor impurity. Another thing is you can see that number of electrons are much higher than the number of holes. This is the punchline for the N-type semiconductor, or you can say electrons are the majority charge carriers. Majority charge carriers. And holes are the minority charge carriers. Remember, this is called as donor impurity. Clear? Now tell me, what is the charge on a N-type semiconductor? Is it positive, negative, or neutral? What is the charge on N-type semiconductor? Very good. N-type means electrons are more, P-type means holes are more. Very good. Okay, so someone of you, Logesh, is saying N-type semiconductor has negative. Everyone is saying the same thing, but you are wrong. Everybody is wrong. When a body acquires negative charge in the electrostatic thing, I think you have studied, when a body loses electrons, then it becomes positively charged. When a body gains electrons, it becomes negatively charged. In this whole situation, what's happening here? Electrons are moving from one band to other band. They are not moving outside the body, and neither they are coming from outside the body, because overall phosphorus is also neutral. If you see, we have added phosphorus only, na? We have not added electrons, we have added phosphorus, which is completely neutral. And in which we have added it in silicon, which is already neutral. You know that, na? Every atom is in neutral state generally until it is excited, one electron is removed from it. So all these atoms are neutral. So when you mix them, so N-type semiconductor has no charge. It is just charge or electrons being transferred from one band to other band. They are not leaving the body. When the electrons leaves the body, only then charge comes. So one point is clear. N-type semiconductor are neutral. You can say they are neutral in nature. This is a very important part. Na? So I think on this screen, the things are clear. Why it is called donor impurity, which impurity is to be added. If someone says uh, arsenic is mixed, arsenic is mixed in the intrinsic semiconductor. So you should know that arsenic is in the 15th group and it will form a pentavalent impurity. Moving further, P-type semiconductor. Now I will not describe it in detail. You know how to explain, how to understand the things. Now I will tell you just one thing. If you add, this is intrinsic semiconductor. If you add some trivalent impurity, if you add, it will become P-type semiconductor. What are the trivalent impurities? That is your 13th group. I think you all know 13th group. Boron, aluminum, gallium, indium, and last is, can anyone answer last is? Boron, aluminum, gallium, boron, aluminum, gallium, indium, and you are saying nitrogen. I think last one is something thallium or something like that. I don't know. You can check the periodic table. It's something, I think, thallium. Okay. Now what happens? This impurity is called as acceptor impurity. I am writing the punchlines only. Yes, sir. Very good, Nisha. Acceptor impurity. Clear? This impurity is called as acceptor impurity. They have 3 electrons in the outer. 13th group means, or trivalent impurity means, they have 3 electrons in the outer shells only. Sometimes it feels like I am teaching chemistry. It's really horrible, actually, subject. I am just teaching. It's not related to chemistry anyway. Okay, so what I am saying, there are only 3 electrons in the outer shell of the trivalent impurities of this 13th group. One more thing, this is acceptor impurity. Now another thing, in this number of holes will be much greater than number of electrons. This is the punchline. Holes are in the valence band and electrons are in the conduction band. You should remember. I think it is clear now. Nothing else. And overall, one more thing, P-type semiconductor, can you say, is it positively charged, negatively charged, or neutral? Can you answer this point? Will it be positively charged, negatively charged, or neutral? Neutral. Very good, Veena. I think you have learned everything. So it is again neutral. Very good. Very good, Nisha. So we have learned these things. After that, now we will move towards another topic, which is conductivity of extrinsic semiconductor. Conductivity of extrinsic semiconductor. Conductivity, you know, I think it is represented by sigma. Everyone knows that. One more thing, it is given by, I am writing the formula. One question is asked in your test that you are taking from the Avanti side. That is E mu H into NH plus mu E into NE. So now someone of you might have confused, or it's like that what's happening here. I will tell you each and every term, write down, because if I write, it will take a longer time. E is the charge of the electron. You know the charge of the electron. Mu is the, H means for a hole. Whenever there is a H in subscript, you can understand it is for hole and E for electrons. Now, mu is the mobility. Mu is mobility. So, mu H will become mobility of holes. Mu E will become mobility of electrons. Now, again, N stands for concentration. Concentration. Ne stands for concentration of electrons, and H stands for concentration of holes. Concentration has a unit per meter cube, per unit volume. In a unit volume, how many electrons are there? This is known as concentration. Someone may call it as electron density or number density. Someone may call it as number density. Someone means the examiner, the question paper may write it as number density. So I think every point is clear. E is the charge of the electron. Charge of electron. This is the conductivity. Now, one more formula that you should remember in this topic, and that formula is very important. Let's understand the situation. Let's suppose this is a pure semiconductor. I'm drawing it a different way. Let's suppose this is a pure semiconductor material, something. In this pure semiconductor, number of electrons and number of holes will be equal. You know that this is pure semiconductor, and this number of electrons and number of holes both are equal. So this is known as intrinsic concentration, Ni. We have given a term Ni to it. Ni means intrinsic concentration, and both are equal. Electrons and holes are equal in pure semiconductor. Now we have added some impurity in it. We have added some impurity. Impurity may be of two types, either pentavalent or trivalent, whatever it will be. The concentration of, if it is pentavalent impurity, then concentration of electron will increase. If it is trivalent, then concentration of hole will increase. You know that thing, because number of holes are more in P-type semiconductor. So now what's happening? After adding impurity, number of electrons becomes Ne and number of holes become Nh. This is for pure semiconductor. This is for extrinsic, or you can say impure semiconductor. So what is the relation? It is Ne into Nh is equals to Ni square. This is the golden relation which can be used to solve numericals, and I have seen a lot of times numericals were asked from this relation. Ne into Nh equals to Ni square, out of which Ni is the intrinsic concentration. I will write it intrinsic density. Same thing is that, concentration or density. Nh is the density of holes in impure semiconductor. Similarly, Ne is the concentration of electrons in impure semiconductor. This formula is to be used a lot of times. I will give you some examples based on that after the completion of this part. Till then, keep this formula in your notebook. We will use that. Moving further. Now here comes a PN junction diode. What is a PN junction diode? PN junction diode is the diffusion, is formed by the diffusion of P-type material into N-type material. Let's suppose this is P-type material, this is N-type material, and they are fused together. It's not like they are placed together. I am not saying the word placed together. They are fused together. So what is it? A semiconductor crystal which has electrons. You can read that. I am not going to read that. What I am saying, listen to me only this time. PN junction is formed by fusing or diffusing P-type and N-type materials together. Clear? The process is something like that. This is a P-type material. on which we have diffused some N-type material. You can clearly see that N-type material is diffused inside it. Now we have placed some metal contact here. This is metal contact. One metal contact is here. These are the two metal contacts. This is how semiconductor is generally formed. Moving further. Now, this is again a very important thing, depletion region, which is to be understood. Okay, I will explain it to you. Now listen to me. Let's suppose this is a PN junction. This is a PN junction. This is P, this is N. They are diffused together. In the P side, which has majority? Answer very quickly. Which has majority? Holes or electrons in the P side? Hole. Very good. So here are holes in the majority. Very good. Very good, Nisha, Logesh. Everyone is quick to respond. And in the N side, electrons are in majority. That's what we know that. Now, when the junction is formed, mark my word, when the junction is formed, there is a concentration difference. There is a concentration difference between electrons and holes in both the sides. One side there is more number of electrons and one side there is less number of electrons. So what happens as soon as the junction is formed, these electrons transfers to the P region. Why they are transferring to the P region? Very good. 1, 2, 3, 4. What kind of name is this? 1, 2, 3, 4. Okay. So these electrons shifts towards the P region. And when these electrons shift towards the P region, what happens next? I will draw another diagram for you. In the N region, some electrons are lost towards the P region. They left the another region, P region. So some positive charge is accumulated here and some negative charge is accumulated this side. Due to this charge formation, one electric field is generated from N side to P side. One electric field is generated. Now, this is P, this is N. One electric field is generated. This electric field opposes the further transfer of charge carriers. This electric field opposes the further transfer of charge carriers, and due to this field, a region is created. A region is created near the junction in which no charge carrier can enter. A region is created in which no charge carrier can enter, and this region is called as depletion region. Now, depletion region is caused by the diffusion of charge carriers. So you can see here, the region near the junction which has no charge carrier is called depletion region. Clear? The width of the depletion region is how much is some micrometer, 10 to the power minus 6 meter of the order of. Now, if there is a electric field, then there will be a potential difference. Let this potential difference is delta V. And this potential difference is called as barrier potential. Why barrier? Because it is opposing the flow of charges. It is opposing the flow of charges. That's why it is called as barrier potential. I think everything is clear on this slide. Moving further. Now this barrier potential has a fixed value. For silicon, it is 0.7 volt, and for germanium, it is 0.3 volt. You don't need to remember that, but if you can, there is no problem with that. Moving further. Now comes a topic biasing. Biasing is again a very important thing. Let me explain you what is biasing. Biasing is the process of moving majority charge carriers using a battery. Is the point clear? The biasing is the process of moving majority charge carriers high potential connect with N-type. Okay. In the previous slide, I think you are talking about. Okay, you are saying that at which point either P or N, which is at high potential. So you know the term, if we move towards the field, the potential decreases. So that means this is at high potential, or you can say high, and this is low. Clear? That's what you are saying. I think you are right, Nisha. You have commented the same thing, na? Very good. Now forward biasing. If I say forward biasing, in short, if I complete this topic, this is a diode. For example, this is P, this is N. When the charge carriers starts moving towards the junction, when the majority charge carriers start moving towards the junction, then it is called as forward biasing. And when they are moving away from the junction, it is called as reverse biasing. I think point is clear. So it has holes, it has electrons. Now, if you connect positive, this is negative. Now, positive of battery is connected to P region, or you can say high potential. Then it is known as forward biasing. You can remember positive of battery with P region, PP, then it will formed, then it will create forward biasing. Point is clear. Now, when forward biasing is created, you have created a forward biasing, then what will happen? One point that will happen, barrier height, this depletion region or barrier potential decreases. Mark these words. They are directly asked. Barrier height decrease. Barrier height means barrier potential kind of thing. Decreases. Another point, depletion region decreases. It becomes smaller because electrons and carriers are forced towards the junction. So depletion region decreases. Next is diffusion current increases. Now tell me, what is diffusion current? Anybody knows what is diffusion current? Diffusion. Okay, someone has mentioned diffusion and drifting. I think 1, 2, 3, 4. Okay. Can you answer what is diffusion current? Okay, 1, 2, 3, 4 is not a good name. You can tell me your name actually, if you are listening to me. What is diffusion current? Listen to me very carefully. The current formed by the diffusion or transfer of majority charge carriers. Okay. I have told you diffusion current is what? The current which is formed by the transfer of majority charge carriers is called diffusion current. Clear this point? Now, as all the holes and electrons are moving like this, so current is forming by the diffusion of majority charge carriers, by the movement of majority charge carriers. So we are saying that diffusion current increases in forward biasing. Next point is drift current remains same. Drift current is due to the I will say movement or transfer of minority charge carriers. So minority charge carriers are not moving, so drift current will remain same. Okay. Direction of current is from P to N. This is again a very important point. Direction of current is from P to N. What is the magnitude of current? Current is of few milliampere only. The current which is formed in this way is of few milliampere. Now one more critical point is coming, and which is resistance of ideal diode in forward biasing in 0, and it behaves as a closed switch. You know the switches, it behaves as a closed switch. Which diode? Ideal diode. In which biasing? forward biasing. Now there is a reverse biasing. Reverse biasing, this is P region, this is N region. Now negative of the battery is connected to P. That means negative is connected to P region. Clear? Or you can say negative means low potential is connected to P region. Then it will be reverse biasing. In this case, what will happen? All opposite things will happen this time. Barrier height increases, depletion region increases, diffusion current decreases, drift current remains same, and direction of current is from N to P. The magnitude of current is what? Few microampere. Mark that. Microampere, and direction is from N to P. And one more point. Resistance of ideal diode in reverse biasing is infinite, and it behaves as open switch. I think every point is clear till now. Now one more topic, VI characteristic of PN junction. VI characteristic of PN junction, you can say that in forward biasing, up to the barrier potential current will not increase, and after the barrier potential current increases rapidly. In reverse biasing, there is negligible amount of current, but after a certain point, the current increases, and this is known as breakdown voltage. Breakdown voltage. This is forward biasing. This is reverse biasing. In reverse biasing, current is due to the minority carriers. You should know that in reverse biasing, current is due to the minority carriers. And here current is due to the majority carriers. Now I think I should take a few questions, or we can take another topic. Okay, this is a question that you can do. Identify forward biasing and reverse biasing diode. Which is forward biased, which is reverse biased? And first of all, answer the first question. Is it forward biased or reverse biased? Tell me. Is it forward biased or reverse biased? How to identify? This is, you can say, high potential. This is, you can say, low potential. Now for forward biasing, okay, do you know the symbol of diode? Reverse. Okay, do you know the symbol of diode? This is the symbol of diode. I think you should know. In this, the triangle represents P region, and this straight line represents N region. This is the symbol of diode. So now, for forward biasing, P region should be connected to high potential, but here P region is connected to low potential. So this is what reverse biased. Very good, Gauri. I think Gauri has answered. Very good. Why you are putting question mark? You should be confident, na? Because in exam, if you are not confident, then you will not be able to answer. You will leave the question. In question number second, if I say, again, tell me. So for which question? Question number 2 you are talking about. In this question, again, you can see that Veena is saying forward biasing. This is -10. This is -5. Which is at higher potential? This is only -5. Reverse biasing. Okay, okay. Low. This is high. So again, this is reverse biasing. Very good. In third example, if I say, this is the symbol of grounding. Grounding means this is zero potential. This is zero potential and this is -5. So again, this is low, this is high. Again, this is reverse biasing. You can clearly see that. Because P region is connected with the negative potential, or you can say low potential. So it will be reverse biasing. That's how we can identify. Now the rectifier thing. Before moving towards the rectifier, let's do some questions here. Okay, answer this question. For a P-type semiconductor, which of the following statement is true? First statement says electrons are the majority carriers. As soon as I see P-type semiconductor, the first thing I will see that electrons are majority carriers, I will cancel it. Option C, option D. Two answers are there. So let's jump to option C. Okay, one more answer, C. Veena is also saying V. So let's check. Okay, one more. See, everyone is saying C. So, okay. 1 and 2 are already cancelled because electrons are the majority carriers. This is wrong statement completely. Now C says holes are the majority carriers. Very good. This is good. And trivalent atoms are the dopants. D says holes are the majority carriers and pentavalent atoms are the dopants. So you can clearly see that in P-type semiconductor, which impurity we add? We add a trivalent impurity. And holes are the majority carriers. So option C is completely correct. Very good, everyone. Now we can move further for another question. One more question I will take here. Okay. In the given figure, a diode D is connected to an external resistance. This is a diode D which is connected to external resistance which is of 100 ohm. This is not watt, this is ohm. Typo hai. And an EMF of 3.5 volt. This is EMF. If the barrier potential developed across the diode is 0.5 volt, that means 0.5 volt is its barrier potential. The current in the circuit will be. So they are asking the current. One very important thing is that 0.5 volt is used by the diode. Is used by the diode. Out of what? Out of 3.5 volt. So the remaining potential across this 100 ohm resistor will be 3 volt. Is this thing clear? 0.5 volt is taken by the diode and 3 volt will be remaining for the 100 ohm resistor. So current in the resistor is I is equals to, you can say, V by R. V is what? 3 volt. Resistance is what? 100 ohm. Can you see that it will be 3 into 10 raised to the power minus 2 ampere? But answers are in milliampere. So which option is going to be correct? That will be 30 milliampere. You can write it as 30 milliampere. So which option is correct? 30 milliampere, which is option number C. I think uh, that's it for today's class. In the next class, we will cover some logic gates, rectifier thing, and some part of transistors and some questions as well. So till now, I think everything is clear. Should I end? Dilip is also saying C. Very good, Dilip. Okay, everyone. Bye. Take care. Okay, thank you, everyone. Thank you, Nisha.